Calc students. Here we are trying to figure out the mysteries of the derivative. The whole point of the derivative in this chapter on derivatives is to figure out how fast a function is changing at a given point. We've been used to doing the slopes of lines, but now can we do a slope of a curve? Well, our best bet so far has been to do the secant line, and that's where the difference quotient comes from. Notice how I've gotten here the f of x plus h and x plus h and f of x and x. X comma f of x is the same thing as x comma y. Now what we do is we move over h and get to a new value of x and look at f of x plus h as a new value of y. And so as you can see in green here, this slope, represented in brown here by 3.2, is the slope of the secant line. And as I bring this second point closer and closer and closer to 1, 1, I get a smaller and smaller slope, and then it seems to be changing less and less as I get closer. Oh, do you see that happen? Right when I get to 1, though, it gets undefined. Because when I take the difference over the difference y or difference in x, it's 0 over 0, indeterminate. So we look at the limit process to find out what the actual slope of the secant line is, right there. The slope of the secant line turn into a tangent line. Because a secant line, like a secant to a circle, is something that goes through 2 points on the circle. The tangent line is just supposed to go through 1 point. How do we get the tangent line then? Well, that's where the limit process comes into play. So let's look at algebraically now, in terms of the notes. And sorry, I wasn't on the right page. Here's the first page. Here we go, the derivative. Tangent line to a curve at a point, the limit definition to find that derivative, and we'll talk about differentiability and continuity a little later on. Here goes. I talked about this before, the idea of a tangent line to a circle, but now when we do a tangent line on a function, it's a similar concept where you cross at one point and you estimate the sort of direction of the function at that point. Notice here we have a tangent line that actually crosses the function again over here, but in this general area right around in here, around P, the tangent line is the best approximation to the curve at that point, and so it gives the rate of change of the curve at that point. Now, we can use tangent lines on a graph, but let's do this exploration. I went ahead and did this up in GeoGebra. On the left here, I didn't really get enough precision to really tell which one is the best tangent line, but if you look over here, clearly it looks like this steepest slope one is the best tangent line, and that ends up being 3x minus 5 for this point at 0. Now, here's the difference between the secant line, which is just your old traditional slope formula, y2 minus y1 over x2 minus x1. And then we do it into the change in y over the change in x. So that's where this f of c plus delta x minus f of c over delta x comes from. Or you could put an x in there too. You could say f of x plus delta x minus f of x over delta x. The difference quotient then is what we call this, because it's a quotient, a division of differences. And delta x, even though it doesn't look like a difference, is actually a difference. It's the x2 minus x1. Here's a nice diagram of delta x, x and delta x and so forth, and the secant line that goes through those. Now we're going to take it one more step and let this delta x go to 0, so that instead of just a secant line, it'll give us the slope of the tangent line. Okay, so the slope of the tangent line of the graph of the point, graph of f at the point c comma f of c is also called the slope of the graph of f at x equals c. Let's try one of these now. Here we go. Find the slope of this graph of f of x equals 2x minus 3 at the point 2 comma 1. Well, I think you already know what the answer is. You've known the slopes of the graphs of linear functions. It's just the coefficient on x. But we're going to see that's consistent with the definition here. We go that the derivative, f prime of c, will equal the limit as x goes to c, backing up to the definition we just talked about here. So we're going to use the delta x definition. As delta x goes to 0, of f of c plus delta x minus f of c over delta x. In this case, it's the 0.21. So c equals 2, and f of c equals 1. When you put 2 into the formula, 2 times 2 minus 3 is 1. So this limit becomes the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 over delta x. Now, as you saw in our last chapter, if you try and evaluate this now, you're going to get f of 2 minus f of 2 over delta x. You're going to get 0 over 0. Ouch. So we go ahead and plug it into the formula. The limit as delta x goes to 0 minus f of 2, which is 1. So we get minus 4 over delta x. So it's the limit as delta x goes to 0 of 2 delta x over delta x. The limit as delta x goes to 0 of 2, which is just 2. So all that just to prove that the slope of the line from the point 2,1 to some point further down is 2. Well, that was obvious, and we had an easier technique. We could have just said right away, in y equals mx plus b, m equals the slope. And it doesn't matter between what 2 points you go on. So in this case, the secant line and the tangent line are the same thing. But, as we're going to see in our next example, they're not. So let's take a look at this one now. The limit, let's make this a little bigger. We're going to try and find the tangent line at negative 1, 2, and also at 0, 1. So let's start at 0, 1. What's the tangent line? It looks like it's horizontal. So the limit at 0, 1, we're going to have c equals 0, and f of c equals f of 1, which is equal to f of 0, which is equal to 0 squared plus 1, which is equal to 1. Right? So now, to find the slope of the tangent line, and the notation we're using right now for this is f prime to indicate the derivative at that point. F prime of c will equal the limit as delta x goes to 0 of f of c plus delta x minus f of c all over delta x. So the limit as delta x goes to 0 of f of c, which is 0, plus delta x, minus f of c, which is 1, all over delta x. Limit as delta x goes to 0 of, let's put in delta x into the function so we get delta x squared plus 1 minus 1 all over delta x. So this is the limit as delta x goes to 0. The 1's cancel, and we get delta x squared all over delta x, which is the limit as delta x goes to 0 of delta x. Now you can plug and chug, and you get 0. If we'd done it any other time, we would have gotten 0 over 0. And so that is basically saying that f prime of 0 equals 0, and that implies that the slope of the tangent line at x equals 0 is 0. It's a horizontal tangent line. And that's what we saw back here. There it is. Horizontal tangent line at x equals 0. Now let's see what happens at negative 1, 2. At negative 1, 2, now we get, for the derivative at negative 1, the limit as delta x goes to 0 of f of negative 1 plus delta x minus f of negative 1 all over delta x. Now remember the function itself, f of x, was x squared plus 1. So we get the limit, the limit as delta x goes to 0 of negative 1 plus delta x squared plus 1. All of that is f of x, negative 1 plus delta x, minus f of negative 1, which is just plain old 2, all over delta x. So it's a limit as delta x goes to 0 of 1 plus negative 2 delta x plus delta x squared plus 1 minus 2 all over delta x. Limit as delta x goes to 0 of, notice how the 1 and 1 minus 2, that's 0, that cancels out. So we just get negative 2 delta x plus delta x squared all over delta x. Now we can divide this delta x in, or you can think of factoring it out. A lot of kids like to factor it out, so let's try it that way. Delta x times negative 2 plus delta x all over delta x. Finally, those cancel out. Up to this point, if we had tried to evaluate the limit, we would get disappointment because we get 0 over 0. But now the limit as delta x goes to 0 of negative 2 plus delta x is just negative 2 plus 0, or negative 2, indicating that the slope of the tangent line equals negative 2 at x equals negative 1. Let's look back at our diagram to check. Sure enough, that's a steep downward slope. Now, as we look at other functions, it gets even trickier. Here's some of the special cases I just want you to be aware of, that if you get a vertical tangent line, we really don't get a derivative. You get an infinite slope because the slope of a vertical line is undefined. So, now here's the definition of the derivative of the function. That is, instead of just finding f prime at c, we can come up with f prime of x. And what we've done in the definition here is replace the c's with x's. So now you can create a whole nother function. And let's take a look at something in something on GeoGebra to kind of give you a sense of where we're going with this. In GeoGebra, your GeoGebra is very handy because you can have it just use this capability right here, to do tangents. You can do tangents to circles and to functions. And so that's how I set up these tangent lines in here. I put a point on the function and then just drew a tangent line through it. So now I can grab this point and have it go all over the place, and we can see that the tangent line keeps changing and the slope keeps changing. And when we reach these peaks, we get a slope of 0 and so forth. And what's going on in here in red is the actual tangent line itself, and in brown is the slope of that tangent line. Here we're trying to get a slope of 0 here. You know, we can do it by, if we do this little trick of, well, no, it's not going to snap to grid, that one, because it's not exactly at an x coordinate. Okay, but we're getting close. Once we can figure out what that slope equals 0, then we can find out where that maximum occurs. Okay, well, what I'm going to do now, though, is for each of these points, I'm going to come up with this point B, which represents a point with the same x-coordinate, but its y-coordinate is the slope. So notice how in B here, negative 1.82 is the slope of the tangent line. And this is how we create a whole nother function. I basically take the same x-coordinate, but then use for y-coordinate the actual slope I'm getting from this formula to come up with this point B. Okay? And there you go. Now, imagine the function that you get if you trace along all those possible B points. Well, that's what we're going to do now with locus of points here. Locus of points is underneath this construction tool, way down at the bottom here, locus. And you have to select the locus point you're trying to make, there, B, but it's based on a point on an object, which is A. And there you go. What does that look like, friends? Notice as I move A around now, you see that B is a point on this shape. That's right, it's a parabola. The derivative of a cubic function ends up being a parabola, and that's one of the basic ideas we have of how to find the derivative quickly. We can lower the power by 1. Okay, so I'm just going to highlight that. So in purple there we've got the derivative. notations now. First, here's what we're going to use over and over again, the definition of the derivative. And in this first sections, I expect you to find the definition using this limit definition. In future sections, from section 2 on, you can use the derivative rules that we'll develop. Here are some of the other notations for derivative. I like using f prime of x a lot. dy over dx emphasizes that this is a change in y over change in x, but it's the infinitesimal change in y over the infinitesimal change in x. That's just some of the notations. That's where the dy dx comes in. The limit as delta x goes to 0 of delta y over delta x. And we have all sorts of ways of expressing that. Now, let's find the derivative by the limit process of this f of x equals x cubed plus 2x. It's a cubic, so just like we saw in our other example on GeoGebra, we expect to get a parabola. So for the derivative, f prime of x, it'll equal the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Now you're going to find that I'm going to switch to h only because the delta x can really be tedious, and a lot of you prefer this when we were working out the limits on WebAssign last chapter, and this works just as well. H is a little easier to write than a delta x, and it's a little easier to do the algebra on. So you get the limit as h goes to 0 of f of x plus h, so it's x plus h cubed plus twice x plus h. All of that is f of x plus h, minus f of x, which is x cubed plus 2x, all over h. Now, make sure you understand this first step. See how what f of x is up here? X cubed plus 2x. F of x plus h is the tricky part. You can't just add an h onto it. You have to put x plus h in wherever you see an x in the original function. That's why it's x plus h cubed plus twice x plus h. Continuing our simplification, the limit as h goes to 0, and I'm going to carry along this limit the whole way because if I evaluate it here, I'm going to get 0 over 0. If I evaluate here, I'm going to get 0 over 0. We've got to wait until this h cancels out to actually do that plug and chug. X plus h cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed. Oh, so that's why we did all that work on Review Pack 1. That's right, so you know how to expand out. 2x plus h cubed. 2 times x plus h is 2x plus 2h. Minus x cubed minus 2x all over h. Here's the fun part now. Things should cancel out nicely for you. We have an x cubed canceling with a negative x cubed. We have a 2x canceling out with a negative 2x. And so you get the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed plus 2h all over h. Notice how everything has an h in it? That's a good thing. Because now you can divide the h into all three of these parts to get 3x squared plus 3xh plus h squared plus 2. And so now as we evaluate the limit, finally we can plug and chug. 3 times x squared plus 3x times 0 plus 0 squared plus 2, and you get 3x squared plus 2. That is the derivative. F prime of x equals 3x squared plus 2. So not only do we get the slope of just the tangent line at one point, this little function here, 3x squared plus 2, tells us the slope of the tangent line at any point x, any point with an x coordinate on the original function. So, using the derivative to find the slope at a point. Now I think, let's go back to the original function. Yeah, this one just asks for the whole derivative function. So the derivative of x cubed plus 2x, let's come up with our summary right here. F prime of x was equal to 3x squared plus 2. And I think you start seeing how you can maybe come up with some rules to do this faster than doing all this limit stuff, and that's the whole point of the next section. Let me know what you come up with on that. Now let's try this next one, a little bit more of a doozer here. Find the slopes of the graph of f at the points 1, 1, and 4, 2, and discuss the behavior at 0, 0. So find f prime of x for fx equals square root of x. So we're going to do this in general first. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. Do you have to memorize this? Probably a good idea. I mean, you can put it on your formula sheets. So we get the square root of x plus h. Notice I put x plus h in for x there. Minus the square root of x all over h. And you did a lot of these, didn't you, in the limit section? Let's multiply by the conjugate. Square root of x plus h plus square root of x over square root of x plus h plus square root of x. And so you get the limit as h goes to 0 of x square root of x plus h squared, so that's x plus h minus square root of x squared is x over h times all that baba. So you get the limit as h goes to 0 of h all over h times all that junk. So that's a limit as h goes to 0. The h is canceled, you get 1 over, let's call that junk up again, it was square root of x plus h plus square root of x. Now we can finally evaluate the limit by plugging and chugging, and we get 1 all over the square root of x plus 0 plus the square root of x, or 1 over 2 square root of x. So this comes in handy. We have that the derivative equals 1 over 2 square root of x. So now we can quickly answer these questions. Find the slopes of the graphs at the point 1, 1 and 4, 2 and at 0, 0. So let's look at these points x, y, and what's the derivative, f prime of x. Well, if we look at 1, 1, we put 1 into the derivative formula, so that's 1 over 2 square root of 1, so it's 1/2. And sure enough, that's what that slope looks like right there, slope about 1/2. At 4, 2, 1 over 2 times the square root of 4 is 1/4. That's what we get there, a slope of 1/4. And x equals 0, y equals 0, the function is defined, the point 0, 0 is defined, but notice what happens, we get 1 over 2 square root of 0, undefined slope. So we actually get a vertical slope going on there. And that's the behavior of the function as we approach 0, 0 from the right. The slopes keep getting steeper and steeper. Because essentially we have half of a sideways parabola here. And so this is the old vertex. And so it would be a vertical tangent line. Okay, find the derivative with respect to t. What happens if we change the variable names on this? So let's, we're going to need a lot of work space here. So the derivative f prime of t, just have to use a different variable now. The limit as h goes to 0 of f of t plus h minus f of t all over h. So it's a limit as h goes to 0 of 2 over t plus h minus 2 over t all over h. And now I would multiply by the overall LCD, the LCD of t times t plus h to get rid of these secondary fractions. And if you remember in the LCD section, this is when you have compound fractions, multiply the top and bottom by the overall LCD. So t times t plus h. When you do that, changes this to the limit as h goes to 0. In one fell swoop, we'll get rid of all our secondary fractions. When I multiply this into here, the t plus h is canceled, and you get 2 times t. Minus, when I multiply t times t plus h into here, 2 over t, the t's cancel, and you get minus twice t plus h, all over h times t plus h. Well, at least we don't have fractions anymore, fractions within fractions. The limit as h goes to 0 of 2t minus 2t minus 2h over h times t plus h. That's a t. So the limit as h goes to 0 of negative 2h over h times t plus h. So finally now that h is canceled, so it's negative 2 over t times t plus h. Now you can plug and chug because you won't get 0 over 0. You get negative 2 over t times t plus 0, or negative 2 over t squared. So that's the derivative, negative 2 over t squared for 2 over t. Now just a little hint, later on we'll write this as 2 times t to the negative 1 power. And you see this power coming down in front, and it to make the negative 2, and t to the negative 1, when we drop it by power, it becomes t to the negative 2, or 1 over t squared. So we're going to have some nice shortcuts later on to all this work. Finally, differentiability and continuity. Basically, it's just saying, well, first of all, you don't have to worry about this alternative definition. And I think I took them all out of the homework. So I'm not going to hold you responsible for that. I do want you aware that there is another way to do it. Instead of having delta x goes to 0, we could have one point come to the other point. And you actually tried some of those with that average rate of change problem from the last chapter. And also just be aware of what happens at a sharp turn like this, because the directional derivatives don't agree. Here, this side says the slope should be 1, this says it's supposed to be -1. So at 2, 0 itself, the function may be defined, but the derivative is not. And you can get vertical tangent lines, that was discussed before, with the cube root function, so that even though the function is defined there and we have a tangent line, the derivative is undefined. Now here's a key idea. D implies C. That's basically how we write it. Differentiability implies continuity. DC, just like our nation's capital. If a function f is differentiable at x equals c, then it must be continuous at x equals c. And that's what we just said. It is possible for a function to be continuous at x equals c and not differentiable at x equals c. So continuity does not imply differentiability. But if it's not continuous, then it is not differentiable. That's sort of the contrapositive of the statement that you might have studied in geometry. If you've got a gap in the function where it's discontinuous, there's no way you can have any tangent line in any derivative. Okay? So there are the exercises. Time to stop.